this problem, we have a skateboarder. Right, this person is skating in this ramp. Notice there is a curvature right there. So the 60 kilograms skateboarder goes down the circular track. If he starts from rest with the angle equals to 0, determine the magnitude of the normal reaction the track exerts on him when the angle is 60 degrees. Neglect his size for the calculation. So we're going to be doing something similar right here. So let's write down the givens. So we have the mass of the skier is 60 kilograms. We have that it starts from rest. So V naught is equal to 0 meters per second. This is at theta equals 0. He starts from the top. And then we know the radius of curvature is 4 meters. Okay, and we're looking for what is the reaction, right, once he is at 60 degrees. So about, we'll say that point. What is the reaction at that point when theta equals to 60 degrees? All right, so once again, let's write down our free body diagram. So with our free body diagram, we're gonna drive for the skateboarder. So we have something like this. So the guy is skating, down the ramp. All right. What forces do we see here? Well, as always, we have the weight, so mass times gravity, or the weights going down. We have the normal force, acting perpendicular to the path of the skating at that instant. And that's all we have here. They don't mention anything about friction, so we don't have to add anything about friction. So we are good right here. All right, and we can write down then our direction. So since this is once again a circular path, we can draw this direction tangent to the path. This will be the u hat t direction, the tangential direction. Towards the center of the curve will be the normal direction. So we can do this in the normal direction as well. All right, so notice we have to break some of these ones into their angles. So because this guy is about 60 degrees down, this will be a zero line. So this is 60 right there. We'll have to break some of this. For example, the normal, we don't have to break it, but the weight, we do have to break it into its components. So the weight will have a component going this direction, and it will have a component going in that direction as well, where the angle of 60 will be here. That will be the angle of 60 right there. All right, so with this, we can then write equations of forces or equations of motion. So if we do sum of forces in the normal direction, this is equal to mass times acceleration in the normal, where we can say that in that direction is positive. So once again, we have then the normal force minus a component of gravity, a component of the weight, and this will be times sine of theta, right, where theta is equals to 60 degrees. And this is equals to the mass, which is 60 kilograms, times the acceleration normal. So with this information, once again, we can plug in this, or we can write it as normal force, which we are looking in here. it's equals to 60 kilograms times the velocity square divided by rho, and this will be plus 60 kilograms times 9.81 meters per second square times sine of 60 degrees. So with this, we should be able to figure out the normal force. It's just a matter of plugging all the information that we have. So once again, we do know rho, so we can replace this for 4 meters. All right. We know everything. The only thing that we do not know at this point is our velocity. So how do we figure out our velocity? Well, we probably need to use the other equation to solve for that. So let me go down a little bit here. And we will do here summation of forces in the tangential direction, where this is positive in that downward direction. And this is equals to mass times acceleration in the tangential direction. So if we plug in the values there, notice that the only forces acting in the tangential direction is that component, a component of the weight. So we will have here mass times gravity times cosine of theta, and this is equals to 60 times acceleration tangential. 60 kilograms, and this mass cancel out, and we can just get here an acceleration tangential. It's equals to gravity times cosine of theta. So if we want to solve velocity out of here, remember we need the velocity, we need to find out a way to get velocity, and we know that tangential acceleration, it's how we get the velocity. So using some of the kinetics equations that we have, because this is a function, right, of theta, we'll have to have here the integral of b dv from 0 to v. I mean, it does that from rest, remember, so we can write that one. And this is equals to the integral, this will be of gravity times cosine of theta. Remember, this will be ds from some s, from 0 to another s. But since we don't have the length s, we need to convert this into a function of theta. We know from the identity, right, that we've seen before, that the position in s is equals to radius times the angle theta. So when you then do ds, this is equals to r d theta. So then we can replace that ds in our integral with the radius, which is 4 d theta. So then this integral right here, we can replace it from ds to the following. So this will be from 0 to 60 degrees cosine theta times 4 d theta, right, from here. So then when you integrate this cosine theta with d theta, you're gonna get over here from this integral, v squared divided by 2 from 0 to v, it's equals to gravity. So I'm just gonna keep it as gravity. Gravity is a constant, so that will be 9.81 times 4, so 4 times gravity times the integral of cosine of theta with respect to theta, that is sine of theta, evaluated from 0 to 60. So once you solve for velocity out of this one, you will get your velocity to be equals to 8.24 meters per second. And from this velocity, if you plug it back here into the normal force equation, it's going to give us a normal force of 1,529.74 newtons. That is the normal force that we'll get out of this one. So notice for this problem, we had to do, equations of motion. We have to do a little bit of the kinematics to solve for the velocity from the acceleration. In this case, we could just not plug because acceleration, it is a function of the angle. It changes as it changes the angle, the tangential acceleration at least. So we need to use some of those variable integrals that we did before. That is it for this video. I'll see you in the next one where we're doing more examples on the normal tangential problems for the equations of motion.